Hi and welcome to Transformers. No, we're not discussing vehicle-changing robots today. Instead, we'll explore an innovative approach for speech recognition using transformer-based models. These models provide high accuracy by effectively modeling long-range dependencies and context, making them ideal for complex languages. Transformers can adapt to different accents, dialects, and noisy environments, enhancing their robustness in various transcription tasks. In this lesson, we'll explore Whisper by OpenAI, a state-of-the-art transformer-based model for speech-to-text transcription. It's pre-trained on vast speech data, making it highly effective for various situations. Whisper's extensive training enables it to handle various speech patterns and contexts, providing accurate transcriptions in challenging environments where simpler models might struggle. We'll use Whisper AI to transcribe the same audio file we previously processed through the Speech Recognition Library and Google Web Speech API, and see if we'll obtain better results. All right. Let's now use Whisper AI to see how it performs. In a new cell in Jupyter Notebook, I'll create a variable and name it model. After the equal sign, I'll type whisper dots followed by the load model function to load the Whisper model. In parentheses, I can specify different model versions depending on the requirements of the task at hand. These versions can be base, small, medium, or large. Here, larger models typically provide better performance at the cost of more computational resources. I'll choose base because this variant provides a good balance between performance and resource requirements. The base model is also one of the most widely used options, serving as a standard for many speech-to-text tasks. Alright, now let's transcribe the audio file with Whisper AI. In the next cell, we'll use Whisper's transcribe function to process our audio file. The path I'll indicate in the parentheses. Let's store the transcription in a variable called result. If you receive a user warning after executing the cell, don't worry. This warning indicates that your system doesn't have a compatible GPU or the necessary graphics card drivers installed so that the model will run on the CPU instead. While a GPU can significantly speed up the processing time, the model will still function correctly on a CPU with slightly slower performance. The result variable contains a dictionary containing information about the transcription process. For now, I'll access the value associated with the key text and store it in a separate variable, making it available for later use. Okay, let's execute. Beautiful, a great-looking text with punctuation. My name is still spelled a bit oddly, but that's not a major issue. The rest of the text seems accurate and well-formed, and the verb turn is in its proper past tense form, turned. Perfect. As we see, the key text holds the actual transcribed text of the audio file. But as mentioned, other keys also bring information about the file. For instance, the key language automatically detects the language used in the audio file. Let's try it out. English. Good. It got that right. What's left is to evaluate the transcript using the well-known metrics WER and CER. Copy and paste the text from above, substituting the variable containing the transcript. Then execute. Wow, these are much better results. The transcription is significantly more accurate than the previous one, with fewer word recognition errors and character placement. This improvement demonstrates the effectiveness of using Whisper AI for speech-to-text tasks. Excellent. But let's look at what happened behind the scenes. Number 1, pre-processing. First, the audio is normalized, meaning the volume is adjusted for consistency, ensuring that quieter and louder parts of the recording are processed evenly. Next, the audio is converted into a MEL spectrogram using the MEL scale. As we previously said, the MEL scale spaces out frequencies in a way that reflects human hearing, focusing more on lower frequencies, which we are more sensitive to. Using the scale, the model captures audio in a way that better aligns with how we naturally perceive sound, which helps it more effectively identify patterns in speech. Number 2. Acoustic modeling encoder. After that, Whisper's transformer-based encoder analyzes the MEL spectrogram and converts it into a latent representation. This compressed audio version retains the key characteristics of the speech, such as phonemes. Although it doesn't look like the original waveform or spectrogram, the latent representation captures all the essential sound features the model needs to understand the speech content. Number 3. Language modeling decoder. Finally, Whisper uses its transformer decoder to convert the latent representation into text. The decoder uses context to determine which words make sense in the transcription. For example, in the sentence, "My name is Ivan and I am excited to have you as part of our learning community," the model understands the surrounding words and structures to generate the text. It knows that Ivan is a name, right? But it can sometimes make mistakes. In this case, the model incorrectly transcribed Ivan as Yvonne, likely because Yvonne is a more common name in its training data. The context helps the model produce most accurately transcriptions even with these rare errors. The model also uses context in sentences like, "I'm a sound engineer turned data scientist," where it knows engineer is more appropriate than a similar sounding word like energy. It also understands that considering the rest of the sentence, putting the verb turn in the past tense makes more sense. The decoder continually uses the relationship between words to ensure the transcription is logical within the flow of the sentence. Number 4. Post-processing. Finally, Whisper does some post-processing to clean up the transcription, including normalizing punctuation, capitalizing sentences, and handling special characters to make the text more readable. Alright everyone, with another essential tool for speech recognition now at our disposal, we can wrap up this lesson. In the next one, we'll learn how to transcribe multiple audio files simultaneously and save the results in a table, a crucial skill for working with real-world datasets. As always, thanks for watching. Hello again. By now, we've covered a lot of ground in speech recognition. We've even transcribed an audio file using the Speech Recognition Library and OpenAI's transformer-based Whisper model. But within companies, audio data is often stored as multiple files, whether it's recorded phone calls, customer conversations, or interviews. As a data scientist, analyst, or audio professional, handling and transcribing multiple audio files simultaneously is not just a nice-to-have skill, it's essential. This ability is crucial when dealing with large datasets, allowing you to efficiently convert vast amounts of audio information into accessible text data. It opens the door to advanced techniques like sentiment analysis, training machine learning models, and transforming unstructured audio into structured text, simplifying the process of extracting insights and making data-driven decisions. Okay, let's move on and see how you can streamline this task. First, specify the path to the directory where all audio files are stored. You can download the necessary files from the Resources section in this lesson. We'll transcribe only 8 audio files for this demonstration to show you the technique. In real-world scenarios, however, you'll likely be working with many more recordings, tens or even hundreds at once. Our method is identical whether you have 8 or 800 files. In this lesson, we'll describe the overall approach which you can easily apply to larger datasets. Okay. Now, type the path to your directory and store it as a string in a variable named directory path. Doing so lets us quickly reference the directory location throughout our code without writing it each time. Useful, hey? This is the path to my folder, but feel free to adjust it to match your own. Next, we'll define a function to handle the transcription process for all the files in the directory. In a new cell, type def, then the name of the function, followed by the required parentheses, where we'll place the variable containing the path to the desired directory. Here, the transcribe directory whisper function takes the directory path variable as its argument, and it will look inside the specified directory. Then it will find all the WAV files and transcribe them individually. But to do this, we need to type a bit more code. We'll first create an empty list called transcriptions, which will store the transcription results for each audio file. Each entry in the list will be a dictionary storing the file name and its corresponding transcription. To achieve this, we'll use a for loop to iterate through all the files in the dictionary. We'll employ the list_dir function from the OS module to retrieve the names of all files in the directory. Inside the loop, we'll add a condition to process only WAV files. With the help of the ends_with function, this if statement will check if the file name ends with WAV. If it does, the code inside of the if block will be executed. If not, the file will be skipped. Okay, what's next? For each WAV file, we need to construct the full path to the file using os.path.join. As arguments to the function, we'll combine the directory path and the file name to create a complete path that points to the exact location of the audio file. Store the result in a separate variable called filesPath. Now, with the path in hand, we can transcribe the audio file using the Whisper model. Type results followed by an equal sign, then model.transcribe, and the filesPath variable as an argument to the function. On the next line, we'll extract the actual transcribed text from the result using the text key, just like we did in our previous lesson. Save this text in a variable named transcription. Finally, we'll append the text and the file name to the transcriptions list. Each dictionary will contain the file name as the key and the transcription as its corresponding value. After the loop finishes processing all the files, the function will return the complete list of transcriptions. Great! To get the transcriptions for all the audio files, we can run the function in a separate cell and pass the directory's path as an argument. Let's display the transcriptions variable and wait for the result. Excellent! We can now see the name of each track alongside its corresponding transcription, and everything looks spot on. Great job! With this, we can conclude the lesson, but there's more to come. In the next one, we'll demonstrate how to store these transcriptions in a CSV file, making them ready for further analysis and experiments. Thanks for watching, and see you soon. Welcome back. This lesson explores how to save audio transcriptions as a CSV file, a crucial skill for anyone working with large volumes of audio data. Storing your transcriptions in a CSV format organizes your data and makes it easier to analyze, share, and integrate with other tools and software. Whether you're performing sentiment analysis, training machine learning models, or simply managing a database of transcriptions, having your data in a structured and accessible format is essential. So, let's go. In a new cell, we'll define the name of the CSV file where we want to save our transcriptions. I'll name the file transcriptions.csv and store it in an output file. Unless we specify a different path, this file will be created in the same directory where the script runs. Next, open the file using Python's built-in open function. Mode equals W indicates that we're opening the file in write mode. Be careful here. Choosing this mode implies that if the file already exists with some information stored inside, it will be entirely overwritten. But this could also come in handy. I overwrote this file many times while experimenting, and I believe you'll do the same. Okay. Setting the new line argument to a blank space ensures the CSV file is formatted correctly without extra blank lines between rows. Finally, let's include the with statement at the beginning of the line to open the file and automatically close it when done, ensuring that no resources are left hanging. In the next line, we'll create a CSV writer object using the respective Python module. The writer function takes the file object as an argument and prepares it for writing rows of data into the CSV file. Logically, the first row will be a header row, which labels the columns. Use the WriteRow method to write this header row to the object. Next, I'll create a list as an argument to the function. The strings track number, file name, and transcription here represent the names of the feature each transcription will have. All right. So far, we prepared a CSV writer and set up the header row. Now, we need to write the actual data into the CSV file. For this purpose, we'll use another for loop to iterate through the list of transcriptions. So type for, number, then a comma, and include a second iterator called transcription, representing the current dictionary from the transcriptions list. Proceed by typing in enumerate. The enumerate function helps us iterate over the list while recording the track number. So, as arguments, pass the transcriptions list of dictionaries followed by start equals 1 to ensure that our track numbering begins at 1 instead of 0. Next, we'll again use the WriteRow method to add a new row to the CSV file for each transcription in the loop. As arguments, we'll first pass the track number, which indicates the position of the audio file in our list. This helps us keep track of which transcription corresponds to which file. After that, we'll pass transcription and specify file name in brackets, which retrieves the audio file's name from the dictionary. This ensures that the file name is correctly listed in our CSV. Finally, we'll pass the same iterator followed by transcription in brackets, retrieving the transcribed text from the dictionary. By passing these three arguments, we ensure that each row in our CSV file contains a well-organized track number, file name, and transcription text. Great! All that remains is to run the code and check the results. After executing the cell, I'll navigate to the desired directory and check for a CSV file. Yes, there is. Cool. Let's now open the file and see if everything's how it should be inside. It looks good, doesn't it? We can clearly see the track number, the name of each file, and the corresponding transcription, exactly as we wanted. This is a powerful skill you've just acquired. By structuring your transcriptions in a CSV file, you organize your data and set the stage for deeper analysis. This method is applicable whether you're working with a few files or a massive dataset. Once your transcriptions are neatly arranged like this, you can efficiently perform sentiment analysis and keyword extraction, or even use the data to train other machine learning models. Exciting, eh? Welcome to the concluding lesson of our practical example section in the speech recognition course. Throughout this section, we've explored two essential methods for converting speech to text. But in this final lesson, we'll switch gears and briefly discuss the reverse process, text-to-speech or TTS. While our primary focus has been on speech-to-text, there are many scenarios where converting text back to speech is incredibly useful. Text-to-speech can be employed in various applications, including virtual assistants, AI-driven chatbots, assistive technologies for people with visual impairments, language learning, content creation, and others. So, how about I demonstrate an easy way to implement a text-to-speech tool in Jupyter Notebook? For this purpose, we'll use the Google Text-to-Speech or GTTS library, a popular and easy-to-use Python library that interfaces with Google's Text-to-Speech API. It's a fantastic tool to convert text into speech quickly, and it's free to use. Okay, I'll create a new variable, text, to store the string content for the tool to pronounce. Then I'll initialize a variable called TTS to store an instance of the GTTS class from the Google Text-to-Speech library. I'll pass two critical arguments to this class: text, which is the string of the text we want to convert, and language, specifying that the language of the text is English. Next, I'll use the save method on the TTS variable to save the generated speech into an audio file. I'll name this file output.mp3. This method takes the generated speech data and writes it to the specified file, creating an MP3 audio file. Finally, I'll use the system function from the OS module to play the newly created audio file. By running the command start output.mp3, the system will automatically open the default media player and play the output MP3 file, allowing us to hear the spoken version of the text. As the final step of this lesson, let's execute and hear the audio file we've just created.
Thank you for taking the time to watch our course on speech recognition. This concludes the final lesson of this section. See you soon.
Indeed, this ends our practical section. With just a bit more enthusiasm, that could make for a great conclusion. Using Jupyter Notebook, we've explored the essentials of audio processing, demonstrated how to transcribe an audio file using two different methods, tackled background noise, visualized the spectrogram, evaluated transcription accuracy, transcribed multiple audio files simultaneously, and stored the results in a table. We even reversed the process by showcasing an easy text-to-speech method. This gives you a solid foundation in speech recognition. In the next section, we'll wrap up this topic and discuss modern practices, challenges, and limitations. See you there.